Today, let's cover topic 8.9, which is the disk method for surfaces of revolution. And what we're doing here is we are now rotating, and this visual here gives us a pretty good idea of what's happening. We are rotating a function around the x-axis. So you can, this right here is the x-axis on your picture, all right? And so we have taken this function, the square root of 4 minus x, and we have rotated it around the x-axis and filled it in with some goop or some goo to make it an actual solid. All right? Or maybe we poured a molten metal in there and let it harden and cool. But we made a solid, okay, by that. And so we're going to find the volume of this resulting solid, all right? Well, so what we're doing is when I rotate this, here's the square, what is the square root of 4 minus x, okay? Well, it looks like this. All right, that's the square root of 4 minus x. It's a square root function that's been moved and reflected. All right, and we're rotating it around the x-axis, which means it's going to have some changing radiuses, or radii, I guess, would be the more appropriate thing. What we're going to use to find this is we are going to slice off a disk. You could think like a quarter, you know, the item of money. If we sliced off here, sliced this thing off, what we're going to wind up with is a very flat cylinder or a disk. And so what we're going to do with that disk, how would I find the volume of any cylinder? It would be pi r squared h. Here's my h, and here's my radius. That's how we would find the volume of any old cylinder. But remember, this disk, this quarter, is laying flat. We actually sliced it vertically. So my radius is going to be my function value in this case. So my height, we are going to slice an infinite number of disks. So my height is going to turn into my dx, just like we've been doing with some other problems in this unit. My radius is going to be my function value, 4 minus the square root of 4 minus x. But we're going to square it, and we're going to multiply it by pi. So because we are summing up all of those little disks, we're going to use an integral. We're going to go from 0 to 4. The reason we're going from 0 to 4 is because that is my x-intercept over there. And we are squaring the square root of 4 minus x dx. So really, in terms of our calculus work, it's not bad. I'm squaring a square root. This is going to turn into pi times the integral from 0 to 4 of just plain old 4 minus x And remember that we need to be able to find antiderivatives. We cannot always rely on Math 9. Half of the AP exam is without a calculator. So my antiderivative here would be 4x minus x squared over 2 evaluated from 0 to 4, but don't forget we're going to multiply that whole thing by pi. So, plugging in my 4, pi times 16 minus 16 over 2 is 8, and then the rest of it is 0. My answer is going to be 8 pi, which is our correct answer we set over here. Once you understand the setup of these, they're really not that bad so long as, again, you can do your integration. Let's look at another example. So this one, well, they had to get squirrely on us and turn it sideways. That's what they did. This region is bounded by this, the x-axis and the y-axis, but it's revolved this way. This is still a three-dimensional figure, but it is revolved around the y-axis, which means we're going to have to take our function and we're going to have to solve it for x. All right? So I'd multiply both sides by 2. So I have 2y equals 2 minus x quantity cubed. Then I would take the cube root of both sides. So I have the cube root of 2y equals 2 minus x. And so after I do my algebra, I have that x equals 2 minus the cube root of 2y. All right, we're going to need that in a second. Why do we need that? Because that is going to be my radius on this problem. Because this one is sideways. Because my discs are going to run, they're going to be cut this way. So that is my radius. From that point on, it's just like the last problem. My volume is going to be pi times the integral of that radius, 2 minus the cube root of 2y squared dy. My limits of integration are 0 to 4. And you can see that from the graph, or we could have done it algebraically. All right. And by setting, we would have to set x equal to 0 to do that, by the way. And then we just plug this. Let's do this one on the TI-84. So we will use Math 9. We're going to go from 0. One of the things you got to pay attention on these problems is don't forget to multiply by pi at the end. All right, that's a very common mistake. So we've got 2 minus the cube root, which is Math 4, of 2x. That thing needs to be, that quantity needs to be squared. Dx, enter, multiply that by pi, and we get our correct answer of 5. How should we write that? That's good review for us. Rounded or truncated to 3 decimal places, 5.026, or I could say 5.027. Rounded or truncated to 3 decimal places. All right. Now, let's look at this next example. And I would like, if you are watching this video online, I would like for you to pause the video and try to get this one set up on your own. All right, you've had a chance to take a look at this problem. I do think it's important on these problems to have a little idea of what the functions look like. All right, so this particular cubic has been shifted and to the, it actually winds up being to the right 2. Just wanted to put this up here real quick for you. So that's the cubic that we're dealing with, all right? And so it does have an intersect here at 2, all right? So we do need to have a pretty decent graph for these so that we know what we're dealing with. So this one is decreasing. It's intersecting at 2. All right, so my slices, this thing is rotated like this, and my slices are running this way. So my radius is just the function value. This one's fairly basic. My radius is the function value. Our volume is going to be pi times the integral from 0 to 2 of that 1/2 2 minus x cubed. All of that is going to be squared. All right, and then multiplied by pi. Now we could clean that up a little bit before we put it into our graphing calculator, I suppose. This is basically going to be a 1/4, so I'm going to have a pi fourths, all right, integral from 0 to 2 of 2 minus x all to the 6th power. That would clean up what you have to put into the graphing calculator, and your correct answer should be 14.3615 when you put that in. All right. Now, one of the things that fits with the disk method is the washer method. And I want to go ahead and introduce this concept in this video because the washer method this is topic 8.11 and 8.12. The washer method just means we've got to subtract a hole. All right, there's going to be a hole in the middle of our solid. So let's take a look at this problem here. This will help us get started. So we've got a region we've got 2 square roots of x as our function. We have the horizontal line y equals 4. So there's y equals 4. And the y-axis, this region in here, is what we are rotating around the x-axis. And so if you look, what's happening we're going to have, because we are rotating this region right here, it's going to be a lot like a bowl in the middle. If you think of a bowl with vertical sides, all right, that's the region that we're talking about. The middle this part in here is empty. All right, there's an opening in the middle. I suppose I could shade some of that with another color to kind of give you the idea that this middle down in here is empty. All right, so it's the same formula. All right, but we have a radius from, let me get a different color here. We have an outer radius and we have an inner radius. So when I slice this thing now, when I slice a piece off of this figure, what I'm going to get is a washer, like you would put around a bolt. And so there's a hole in the middle. It is the same exact problem as what we did before, all right? But now we need to subtract outer minus inner, all right? So on this problem, let me insert another page here. My outer radius is the constant function. All right? So my outer is 4. My inner is 2 square roots of x. So my volume works out just like before. I'm going to have a pi out in front. But I'm going to have the outer radius squared minus the inner radius squared dx. My limits of integration, I need to ask, when is 2 square roots of x equal to 4? So I have the square root of x equals 2. So that's going to be 4. All right? So my limits of integration are from 0 to 4. Cleaning this up, I've got pi times the integral from 0 to 4 of 16 minus 4x dx. So our antiderivative, we need to remember that we have a pi in front of it, and we're going to have 16x minus 2x squared evaluated from 0 to 4. And so we're going to have a pi times a 64 minus 4 squared is 16 minus 32. And the rest of it is minus 0. So we're going to have 32 pi. Okay, as our answer. So the idea is subtract the middle, and remember that we could be rotating around the y-axis. And we know how to deal with that. If we're rotating around the y-axis, we know we're going to have to take our function and we're going to have to solve it for y. So x equals the cube root of y. All right? So we've got this cubic. It's rotated. Now let's look what else we have here. It's also bounded by x equals 2. So this is my region that's being rotated. The reason for the picture is so that I know what my outer and inner functions are. This is what's being rotated. So my outer radius is 2. The inner radius is the cube root of y. All right, so my setup is pi times my integral of, we'll come back to the limits in a second, the outer radius squared minus the inner radius squared, that's y to the 1/3 squared dy. All right, and so my limits of integration need to be y values, so I'm setting x cubed. When is x cubed equal, I'm looking for, if I put in a 2 value, I'm going to get 8. So this is from 0 to 8. And there's my setup. And when we do that on the TI-84, we get a value of 40.212. That problem is not out of the realm of possibility, though, for an antiderivative. We need to be able to do that one analytically as well. And we will stop there for today.